So in the last video, we derived the logistic model, and that was a heavy video on integration. Now we're going to actually use it in practice. So just as a review, before we developed it, if we have the derivative being equal to the following, we can get this equation: y equals L over 1 plus a times e to the negative kx, where a equals L minus y naught over y naught, and L is your limiting amount. Or in other words, it's the max that your y gets close to but doesn't equal. So given this, if we wanted to solve this equation, really we're just looking to put the pieces together. So how do we start? Well, I'll start off like this. Looking at our equation that we're given, y prime equals 0.08 y 1 minus y over 1,000. And looking at what that means, we know right away that L equals 1,000. And we know that K equals 0.08. We know that my initial y value is 100. So therefore my A value must be L, which is 1,000, minus y naught over y naught, which is 9. So now I know L, I know K, and I know A. Since I know all those things, I can now write my equation that y equals L, well, we know that's 1,000, over 1 plus A, we know that's 9, e to the negative k, k is 0.08x, and there is my equation. So really this is just to say that since we have derived the logistic equation, since we've already done that derivation, anytime you now get this differential equation which falls under logistic form, we don't need to do any rederiving. We can just find the constants and get our equation. All right, let's look at some more problems. Now we're given the logistic model, and we're going to be asked a couple of questions. The first one: find the limit as x approaches negative infinity. Well, this is a little bit ugly math, but I'm going to actually substitute negative infinity. So we got 50 over 1 plus 4 times e to the negative 0.2 negative infinity. Now, we've got a negative and a negative down here. That's going to be positive. This is going to be e raised to a huge number. So essentially, we can think of that as like 50 over 1 plus 4 times e to a huge number, which is like 4 times infinity. So this is, again, essentially 50 over a huge number, which is close to 0. So the limit as x approaches negative infinity of f of x equals 0. What about as x approaches positive infinity? Well, let's do the same kind of ugly method again. Let's put it in positive infinity. And we get 50 over 1 plus 4 e to the negative 0.2 infinity, which equals 50 over 1 plus 4 times e to a essentially negative infinity, which is 50 over 1 plus 4 times 1 over e to infinity. Using what we know about negative exponents. So 1 over a huge number is essentially 0. So this is essentially 0. So we get that this equals 50 over 1, which is 50. So the limit as x approaches positive infinity of our function is 50. And that's what we should expect, because as x gets close to positive infinity, this means that our function approaches its limiting value. And its limiting value is this L. So it makes sense that it's getting close to 50. What about the point of inflection? Well, okay, this is a slightly harder problem, but let's see what we can do. If we were to take this we know that this is the general form of this is y equals L over 1 plus a e to the negative kx, and that the first derivative is y prime equals ky 1 minus y over L. So, and that's just how we derived the logistic model originally. So here's our logistic model, and we know that this is L and that this is K. So therefore we know that our first derivative is K negative 0.2 y times 1 minus y over L, where L is 50. And why do we want that? Oh, well, we want that to find the point of inflection. The point of inflection occurs when y double prime equals 0. So we have the first derivative, but now we're going to find the second derivative. Before we do that, I think it would be easy to expand this. This is the first derivative. So the second derivative, we're going to take the derivative of this. It's negative 0.2 plus 2 is going to drop down. And we're going to get 0.4y over 50. And now we just need to set this equal to 0. We found the second derivative, so we want to know when does this equal 0. So when does our second derivative, values of x, when my second derivative equals 0? Plus 4y over 50. Now we're going to solve this by moving. Well, I guess it's easier to move this over and solve for y. So we get 0.2 equals 0.4 y over 50. And when you solve this for y, we get y equals 25. That tells us that when y equals 25, we're going to have our point of inflection. Well, typically we want not just the y value, but the x value. So we're going to have to go back and find out what will be that corresponding x value. And we'll do that on the next, we'll start a new page. So we just showed that given our function f of x equals 50 over 1 plus 4 e to the negative 0.2 x, that when y equals 25, there's going to be a point of So now we can just set those equals since the numerators are equal, the denominators must be equal. So we get 2 equals 1 plus 4 e to the negative 0.2x. Solving this, moving the 1 over 1, divided by 4, 1/4, taking the ln, and then dividing to isolate x. So it's not pretty. So when x equals that, and when y equals this, we're going to have a point of inflection. So for us to sketch this, well, we know that we're going to have these asymptotes at 50 and 0 because that's what the function approaches. When x equals 0, my function is going to equal f of 0 equals 50 over 1 plus 4, and then e to the 0 is just 1. So 50 over 5, which is 10. So we know we're going to go through this point at 10. And we know that there's going to be a point of inflection when y is 25, and when the corresponding x is ln of 1 over 4, all divided by negative 0.2. So that's a sketch of the graph that includes the y-intercept and the point of inflection. Maybe we could generalize this though. Let's think about if we just had this general form. We wanted to find the point of inflection. So without any numbers, let's find the point of inflection for y, given my first order differential equation. So we're going to use the same sort of derivatives that we just looked at, only now no numbers. So we say y prime equals ky minus ky squared over L. I want to find the second derivative. The second derivative is k minus 2ky over L. And we want to see where that equals 0. So 0 equals k minus 2ky over L. And we're going to solve this for y. So we get 2ky over L equals k, or solving for y equals L over 2. Interesting that the point of inflection is going to occur when y equals half of its limiting amount. And then to find the x value, the corresponding x value, we will do the following. So looking at another sheet, we know that the point of inflection occurs when y equals L over 2, and looking at the general equation for y, we have y equals L over 1 plus a e to the negative kx. So we want to find the x value for the point of inflection. So we're going to plug this in for y. We get L over 2 equals L over 1 plus a e to the negative kx. This should look kind of familiar to you. We're just going to set these equal to each other. So setting those equal to each other, 2 equals 1 plus a e to the negative kx. And I'm going to stop this and set it